G'day everybody. In this lesson we're going to start to talk about discrete distributions. We'll do this lesson in two parts. Today we're going to talk about what a discrete random variable is. We'll look at how we create distribution tables for discrete random variables. We're going to determine the expected value of a discrete random variable, and we'll see how we use the distribution to calculate various probabilities. First of all, what is a discrete random variable? It's a variable that occurs randomly but only takes on a countable number. Counting numbers being 0, 1, 2, 3, 4, etc. as high as you like, but no values in between there. So let's have a look at some examples of variables that are random and occur as countable numbers. Let's say we were thinking about the number of TV screens in a person's home. That's a discrete number. We can count those. There's nothing in between 4 and 5 screens. We don't have 4.5 screens, for example. If we were talking about the number of days on which rain occurs during a week, that would be a discrete random variable. It has a finite range of values. It could be anywhere from 0 to 7 days. Something like taking 3 coins out of my pocket at random and thinking about what the value of those coins would be. That's a discrete variable. This variable doesn't take on the actual counting numbers themselves. They take on monetary values, but those monetary values will be discrete. We don't have the full range of monetary values just for 3 coins. And the example that we'll actually spend a bit of time with in this lesson, what about the difference between 2 dice? If I roll 2 dice, I get 2 random faces popping up. There's a difference between those 2 faces that again is a discrete number. Maybe to show you or to talk about variables that are not discrete, usually we're calling these continuous random variables, and we do look at these later in the course. So for example, if I was to time how long it takes somebody to walk 100 meters, that's a continuous variable. It can take on a range of values from a certain number of minutes to a certain number of minutes and seconds to a half a second. We can measure that as accurately as we like. Things that we measure, like the length of a tree branch, again that's a continuous random variable. Tree branches don't jump from being 30 centimeters long to 31 centimeters long. There's a whole range of values, an infinite number in fact, between 30 and 31. If we were to talk about the temperature of a cup of coffee left in the staff room, again that's something that we measure. Usually things that we measure are continuous random variables. So in this lesson we're going to focus on the discrete variables, things like these, and we'll talk about their distributions. We're going to create a probability distribution table for the difference of 2 dice. So here you can see I've started by defining the variable. They're always capital letters that we use for variables. So I've said let x be the difference of 2 dice. So x is my discrete random variable. Then we set out a table with small x representing all of the possible values that our discrete random variable could take on. So if I throw 2 dice, it could turn out that I get a 1 and a 6, and that's the highest difference I can have. So the difference could be 5, and then it could be 4, it could be 3, 2, 1. If I roll a pair, the difference between those is 0. So I've got 6 distinct or discrete values that random variable can be. And below that, for each of those values, I'm going to express the probability that the difference will be that number. In this case, we could work it out. Here I've got a lattice diagram that shows all of the 36 combinations of 2 dice. So a pair of 1s, a 3 and a 2, a 2 and a 3, a pair of 6s, everything's there. Everything that can happen when we roll 2 dice. I can use this lattice diagram and I can find those probabilities, which in this course is often not what we have to do, but I thought it would be useful to see where those probabilities come from. So this is what those 6 probabilities are. The probability that I throw a pair, or that the difference is 0, is 1 in 6. The probability that the dice just differ by 1, it happens to be 10 out of 36 outcomes, which simplifies to 5/18. And so you can see the probabilities there for each of the differences that I could have. The most unlikely result being if I roll a difference of 5, there's only 2 options out of 36, which is a 1 in 18 chance. So what a distribution table does is it lays out all of the possible values that that random variable can have and the probabilities associated with each one of those variables, each one of those values. 2 properties that all probability distributions have. Their probabilities are always non-negative. That's just a general condition of any probability actually. So all of these values that occur in the row down below have to be non-negative. They could be 0. We can have a distribution table for that includes 0 for one of the variables, one of the values that it takes on, but obviously no negatives. And the second property is that all of the probabilities, regardless of how many there are, need to add up to 1. They should have a sum of 1. That would show that they encompass all of the values that that random variable can take on. Often when we're working with a distribution table, we're interested in something we call the expected value. So it's about knowing what to expect, but it's a little bit more than that. Let's calculate it first, and then I'll talk about what it means. So this expression here, this is a formula, if you like, for the expected value. We use capital E for expected value. We show the variable that we're dealing with. We've got the Greek letter sigma, which means we're going to add up all of these things, and the things that we are adding up is each value of x multiplied by its own probability. And so for our distribution, it looks like this. So you can see when x equals 0, the probability is 1/6. When x equals 1, its probability is 5/18, and so on. And so I've multiplied each value of x by its probability, and I'm finding the sum of all of those products. And we get exactly 35/18, but it might be helpful to round it off, approximate it. It's approximately 1.94. Ironically, to expect 1.94 might seem ridiculous because it's not one of our discrete values. So what our expected value probably is better thought of is as an average. If I was to play this game over and over and over again, I should expect that the average of all of the differences that I roll is 1.94. It's a measure of central tendency of this random distribution. So that's the expected value. We're going to use our distribution table to calculate a few different probabilities, and what I encourage you to pay attention to here is that the way that I write these out, the way that we express these probabilities. So our first one, the probability that the difference is greater than 3, the difference of the 2 dice is greater than 3. So I'm using my random variable x that I've already defined, the probability that it's greater than 3. There are 2 possible values in our distribution that are greater than 3, and that's 4 and 5. And so we can simply add up the probabilities associated with rolling a 4 or a 5. So both of those are greater than 3. So the probability of rolling a difference of 4 is 1/9. The probability of rolling a difference of 5 is 1/18. So the probability of rolling a difference that's greater than 3 is exactly 1 in 6, or 1/6. Let's have a look at the probability of rolling a difference of 2 or less. And so I've expressed that as being the probability that x is less than or equal to 2. And we can see there on the table there are 3 values there from 0 to 2. So adding up each of those probabilities, I've got the probability that I get a difference of 0, a difference of 1, a difference of 2. And you can see the fractions associated with those probabilities, and I get exactly 2/3. So 2/3 is the probability that my difference will be 2 or less. So it's a likely result. What about the probability of rolling a difference of at least 2? So here we can see there are 4 possible values. So to save myself a bit of time here, I'm going to do this one slightly differently. So the probability that x is greater than or equal to 2 is, I'm going to use the complement. I can see that for the probability that x is less than 2, I need to take into account 2 values. If I use the property of the table that all the probabilities add to 1, I can use the complement here. So the probability that x is less than 2 is in these brackets. The probability that the difference is at least 2 would be 1 minus that value, which turns out to be 5/9. So I've used the complement. The complement is a concept in probability that will be very useful over and over again. This is the last question we're going to look at for this distribution, for this lesson in fact. It's a conditional probability. So what is the probability of a difference of 5 given that it's greater than 3? There might be a common sense approach to using this, but I would like to show the expression using the formula for conditional probability. So you can see here I've expressed the probability the way that the question stated. What's the probability that x equals 5 given that x is greater than 3? And so using our formula for conditional probability, we've got an intersection of values, the intersection of the values that are equal to 5 and greater than 3, divided by the probability that x is greater than 3. And that intersection is simply 5. So the overlap of the values that are equal to 5 and the values that are greater than 3 must be just the probability that x equals 5. Dividing that by the probability that x is greater than 3, I've got 1/18 divided by the sum of those two probabilities, 1/9 plus 1/18, and the result of that is 1/3. So we've used this probability distribution as a very handy way of seeing all the probabilities associated with each outcome, each individual outcome, and we've used those to calculate probabilities in different ways. So hopefully now you have an idea of what we mean by a discrete random variable. You certainly will after we compare that to continuous random variables later on. We've seen how we create a distribution table. We've talked about the properties that that table has. We've used the formula for calculating an expected value, which is a measure of central tendency. And finally, we've used our distribution to calculate 4 different probabilities. And you've seen the notation that I've used for each of those. Please write down any questions that you have as a result of this lesson and complete the Google form to log your attendance and to check your understanding. Thanks.